In the last video, we talked about balancing equations. In this video, we're going to talk about moles and how that applies to calculations in chemistry. In the video after this, we're going to talk about moles as applied to a balanced equation. So we're going to have a little bit of a segue here, getting to know what a mole is and getting comfortable with it before we start doing calculations with moles and balanced chemical equations. So you might be wondering, what is a mole? A mole is a unit of measurement that we use a lot of times in chemistry. It's convenient for us because it lets us measure really big numbers of particles, and it tells us how much is present in a substance. So just like the way we count shoes in pairs, how we count eggs by the dozen, we count atoms and molecules in moles. It's just the unit that we use. So whenever you see a balanced chemical equation with these numbers in front of it here, 4, 3, 2, or whatever numbers are in front of each molecule, that is a mole. There are 2 moles of this compound for every 3 moles of this compound. And there are 4 moles of this element for every 3 moles of this, and so on and so forth. So these are relationships of them to each other. We're going to talk about this in the next video. Let's dig into what a mole is. So why do we use moles in general? The reason is because matter consists of an incredibly large number of atoms. Atoms are itsy bitsy tiny, so we need a really big number in order to represent these, because these quantities are just kind of unreasonable. So if you think about how many atoms a itsy bitsy tiny piece of copper contains, it's 1 centimeter by 1 centimeter, so like about this big, a piece of copper wire that's about 1 centimeter long. It contains a bajillion atoms. Okay, I don't even know what that number is. It's huge. It's 10 to the 21st atoms. That is a lot of matter, and it's just hard for us to quantify something that large. So we use the mole to describe this in terms that are easy for us to calculate. So because this number is really inconvenient, we use moles in order to quantify this dozen, essentially, of atoms. So I like to think of it as the egg carton. So if you think about eggs in an egg carton, I'm bad at drawing. Anyways, here's our little egg carton. And our mole is the carton, and the atoms are inside here. So the mole is containing all of these atoms. So the main reason we use the mole is because matter is really small, and that means in a small sample of it, there's a lot of it. And so these numbers are either really big or really small, and we need a good way to describe them. I did want to show you a practical example of kind of why we classify things in moles and how much matter there really is, or how many atoms are really in a sample of matter. So I wanted to talk really briefly about transmission electron microscopy and graphene. So this here is a substance called graphene. You might have heard of it in the news. It is very interesting. It's a carbon-based, it's just carbon molecules that are arranged in a specific format. And what's really cool about graphene is the way that the atoms are oriented. You can kind of see them here in this hexagonal pattern. They are semiconductors, so they conduct electricity, and it's carbon. It's not a metal. Carbon is present all around us. It's really easy to access. Everyone has access to it. It's a renewable material. So this is a really exciting material discovery, and you'll be seeing it actually probably a lot in the news in regards to developing new materials for things like solar panels or semiconductors or computers, this sort of stuff. There's all kinds of research going on graphene. In this picture that you see here, if you see the scale, it says 5 nanometers. That's itsy bitsy tiny, super duper small. And these are actually the individual atoms that you're seeing here. This picture was taken with this transmission electron microscope over here. This is actually what it looks like. It's huge like this. I've used one before. They're enormous. They shoot electrons at your sample, and the electrons bounce off, and that's how it tells you the shape of what you're looking at. You can see that it gets even smaller here. It gets down to 1 nanometer, and it zooms in so we can see our atoms even better right here. 1 nanometer. So this microscope really can view atoms individually, and we can see the scope of how many atoms are in such a small sample, only 5 nanometers. It's hard for us to distinguish individual atoms in a piece of material, even that small. Let's talk about using moles in chemical equations and using them in unit conversion. We use moles a lot in order to describe things on the periodic table. So if you take your mass on the periodic table, we've been talking a lot about molar mass, and say let's look at hydrogen. The molar mass of hydrogen is 1.01. Well, 1.01 what, right? What's the unit on that? The unit on things on the periodic table is grams per mole. So the molar mass of hydrogen is 1.01 grams per every mole of hydrogen that you have. This number is really handy when we are needing to convert from grams to moles and back and forth. So let's use this relationship in order to try this example problem. So I'm going to let you try this calculation on your own. This is just unit conversion. Don't freak out, we're just using a new unit. You will need a periodic table in order to do this. You'll need a periodic table because you're going to need to find the mass, the molar mass of these substances. So for this first one, you're going to use KBr. So you're going to need to find in grams per mole how much the stuff weighs. You can find this from the periodic table. You can add the mass of potassium plus the mass of bromine in order to get your total mass of this compound. So use unit conversion with these values and see if you can find how many moles there are in 2.5 grams of this sample. Let's take a look at how to solve this one. So if we want to find an answer in moles, and once we look at the periodic table, we add up the mass of potassium plus the mass of bromine, we find that altogether this is 119 grams per mole. That's the value there. We're going to use these two numbers in order to cancel out units in order to end up with our moles. So we have 2.5 grams. We want to find out how many moles this is. If we don't want grams in our answer, it needs to go away. So we're going to simply put that on the bottom here. Grams cancels, and we're left with moles. So that tells us that there are 0.021 moles of KBr in this 2.5 gram sample of the salt. Let's try this one more time, but going the other direction. So if you wanted to measure out 0.035 moles of, let's say, sodium chloride instead of potassium bromide, how many grams would that be? So do the same thing here, except kind of going backwards. So you'll need the molar mass of NaCl from the periodic table in order to find grams. Let's take a look at how to solve this problem. So we want to find out how many grams of NaCl this amount of moles would be. So if we start with 0.035 moles, and we need to get to grams, we need to cancel out moles. So we're going to put moles on the bottom. Our mass in the periodic table is grams per mole. So that's where we're going to pull that value from. So if you go to your periodic table and you add up the mass of Na plus Cl, there's only one of each of these. We find that total, this is 58.44 grams per mole. If you had two chlorines, you'd add another chlorine. So if it was like Na, this is not a thing, but if it was NaCl2, it'd be Na plus Cl plus Cl. So do be careful there. I've given you examples with only single atoms there. Okay, so we're going to use this value, and that tells us that 2.05 grams is how much NaCl this many moles are. So if somebody asked us to measure this out on a balance, we go to the balance and measure out 2.05 grams of sodium chloride, because that's how many moles this is.